I'm Sheila Stephenson. I'm the CEO for 1Spatial, and I'm joined by Kevin Sigwart, who is our Director of Solutions. And 1Spatial Inc. is a U.S. company, but we're a wholly owned subsidiary of 1Spatial Group, which is based out of Cambridge, England. And what we want to discuss with you today and share with you is on data governance, because our experience in data management obviously has led us into numerous discussions with many different clients in many different industries around data governance. And so what we want to share today is some of the experiences that really drive to the import of data, of good solid data governance, especially as we move towards enterprise data management, as well as some of the best practices for overcoming some of the challenges that come along with data governance, of which there are plenty. So without further ado, I'm going to pass it over to Kevin Sigwart, Director of Solutions, so that he can share the presentation with you.
All right, thank you very much, Sheila. All right, so yes, as Sheila mentioned, we're going to be talking about how we can leverage tools and technology to enforce data governance throughout the enterprise. But before I get started, I'd like to just start with a personal story. So for those of you who do not know me, Sheila introduced me. I'm Kevin Sigwart. I'm with 1Spatial. I'm the Director of Solutions. But before being at 1Spatial, I was a GIS software developer, and I was working on a contract at the Department of VA. And as part of that project, we were responsible for building out an enterprise GIS that funneled data up from a variety of the different organizations like your National Cemetery Agency, the Health, and the Benefits Group. So we were feeding up all of this facility data into the GIS and then providing a interface for them to view their assets on a map. And then on top of that, what we would do is we would bring in third-party sources like maybe the National Weather Service data sets and infuse the information coming from weather events into those assets. So for example, if there was a hurricane coming, we could tell for any given asset when they would start reaching hurricane force winds. Now this was great. It was they would display this application at their operations center for their emergency management department. And it was a nice interface showing that information, giving them instant feedback on what's going to be affected and when it's going to be affected. So anyhow, the there was a after the application was being used, and then there was an event, right? So there was an event for an active shooter in California. And when they were bringing up the application, which was showing where the facilities were located in proximity of the actual event, they realized that there was missing a facility in that map. And one of the emergency managers decided, like, I'm going to go into my emergency management system and see if there really is a facility, because I think there's a facility there. So they went in, they logged into the emergency management system, they pulled it up, and they noticed that there was a facility that wasn't on the map. So now we're looking at this operational picture and not getting the true value. So even though we have this awesome application that's displaying real-time information, we're losing confidence in our emergency managers because we're not providing the right data in that application. And what we turned out is that there was no connection into that emergency management system. So we had no vision of what's going on in that emergency management system. And this is a prime example of a lack of data governance. We were not aware that there was data being edited in other sources, and we had no way to facilitate to make sure that our system was in sync with the other systems. So that's why there's a need to have data governance, and there also needs to be, not only do you need to set up a data governance structure, but you also need to have a way to actually facilitate the validation of that of those data governance policies that you're setting in place, and making sure that everything is adhering to those standards. So with that, that leads us to data governance, right? So I'm assuming most of the people on this call know what data governance is. It can be a pretty loaded term, but basically what data governance is facilitating what the quality of the data should be, who has access to the data, who can edit the data, and where the data is going to be stored, among other things, right? So you can see in this picture, there's a lot of different aspects of data governance. What I'm really going to focus on today is the quality control aspects, the integration interoperability, and the metadata. And then when we're trying to work with all these data systems, right? Most of the people on this call, we're all GIS experts, right? but we're not always just working inside of a GIS environment. We need to pull data from a variety of other systems, and it can be very complex. You have things like your GIS databases, you have your workflow management systems, CRM systems, CAD systems, and all of these work together, right? You're not going to move everything from CAD into GIS and manage everything in GIS. There's a reason why CAD systems exist, just like there's a reason asset management systems exist. So there needs to be a way to identify, well, where do these systems intersect, and how can we make sure that we are facilitating the data flow properly and making sure that the data in all these systems are kept in sync. And that can be a challenge, as you can see in this slide here. And so one way to solve, or to help solve this problem, is with a concept called location master data management. And this is where we're looking at all of our different application tier, right? We have our CAD systems, the GIS systems, the workflow management systems. All of these have their own metadata. They have their own schemas. And the schemas are going to be different in a GIS system versus your asset management system. They're meant to be doing different things, right? And then technically, each of these GIS systems can also be broken out into your different organizations, right? So then each of those have different ways of managing data and managing the schemas. So what ties all these together are your business rules, right? Your data governance policies for saying where the data should be edited, how the data should flow to these different systems, and what are all those policies to set that all in place. And then lastly, there needs to be a way to orchestrate those workflows. So to make sure that the data is adhering to those data governance policies and making sure that all your data is kept in sync and of the best quality possible. So that leads us to 1Spatial, right? Where at 1Spatial, we focus on data management. Sheila mentioned this in the opening, right? And when we talk about data management, we're really talking about data validation, data integration, and data enhancement. So we have a rules engine, the One Integrated product. It's a rules engine where you define the business rules of your data, and anything that doesn't conform to those business rules gets flagged as we call non-conformances, right? So this can be a lot better or a lot more efficient than trying to do it manually. When you're trying to do it manually, it's very time consuming and it's very subjective. If you're dealing with your entire enterprise, there's no way a group of individuals can go through and in a timely manner, manage and make sure that there's no issues with the data. Typically, the only time you find out that there's an issue with your data is in the case of some sort of emergency event, just like I showed you in that first example. We had no idea that that particular facility was not on the map until there was an actual event that caused us to realize that it was missing. So we can perform those validation checks to make sure that the data is fit for purpose. But what's an added value is the fact that we can not only validate the data, but we can connect into multiple different sources. So we're not limited to one GIS database. We can connect into multiple geospatial databases, or we can start to connect into other business systems. Like you may have CAD data, or you may have your asset management systems, your CRM systems. We have the ability to integrate with those systems, connect into them, and allow the engine to write validation rules across your entire enterprise. And lastly, the engine provides the ability to automate the process of cleaning the data. So when it identifies an issue, if you have the data governance set up, you can tell the system, well, I know that if an asset is missing in this system, but it is being edited in this other system, facilitate to push that information from the one to the other, right? And a variety of other things, right? So, and I'm going to get into highlighting some of these examples in the demonstration section of my presentation. And we're going to talk a little bit more about how we can automate the cleaning of the data, how we can do things like conflation and bringing in other data sources like non-spatial systems and other CAD-based systems. And that leads us to some of our clients, right? So I said that we have, at 1Spatial, we have 45 plus years in developing data management solutions. In the US, we've been operating for about 5 to 6 years now. And we've been working with a number of different clients on automating the process of doing their quality control, performing validations and data cleanup. And most of these clients over here in this section of the slide right here, we're mostly focusing on their GIS data sets and their GIS databases. And this is everywhere from the federal level at like federal highways where we're doing HPMS validations, NOAA dealing with their electronic nautical charts, to the state level working with transportation agencies, getting the data clean before going into roads and highways, or just making sure their data is clean and fit for purpose. And then lastly, down to the county level. So working with counties like LA County on validating their data to make sure that their data is ready for 911 or E9 or next gen 911. But then, we have other clients where we're doing not just validation, but we're also doing change detection and conflation. So facilitating that data rollup process. And one of the prime examples, and if you've seen one of our presentations before, we probably talked about it, but with the US Census project, where we're taking the Tiger centerline data, and we are facilitating the change detection and the conflation of 3,200 different data providers. They submit the data up, we perform validation of that data set, the change detection, and then the conflation process to determine what's different between these different data sets. So those were all those examples. These are very GIS-centric examples, but we've also done stuff with CAD data. So we've done CAD and asset validation, and we're currently doing a project right now at Google where we're validating the CAD drawings for their my tongue is twisting up a lot. Real estate worldwide services group. So validating the CAD drawings for the real estate holdings and their asset management system, Tririga. Now these are where we're looking at different systems, right? But then we've also worked with some clients on what we call master data management. So taking not just the GIS, not just the CAD, but the asset management system, and making sure that all of that is facilitated and playing together. And we've done that a lot in Europe at the Ordnance Survey Ireland, and Network Rail. So with that, I'm going to show some examples of some of these use cases of doing this type of work. So the first thing we're going to talk about is enforcing data governance through validation, right? And in this case here, you may have a data governance policy saying that your road data must be routable. But what does that actually mean, right? You can say that the data must be routable, but then you have to define what business rules make it so that a road data set or a road segment data set is routable. Well, one, you have to make sure that the road name is actually populated, right? If you are using some sort of navigation software, you don't want to say turn right at Null, right? You want to make sure that it's going to tell you which road you need to turn at. You also want to make sure that there's no sort of geometric issues in the data set, like kickbacks and spikes, that can mess up the length and the distance calculations. You must make sure that's connected, right? You can't have overshoots or undershoots. You got to make sure that a road geometry is actually connected at the start or the end of another line segment. So it's split at your line segments. You can't turn right if the segment's not actually split at that particular point. You can make sure your address ranges are correct. They can't have overlapping address ranges. How is it going to geocode where it needs to go if the address ranges are overlapping? Now, that was an example of row data, right? But what about parcel data sets, right? You may have a governance policy saying, well, I don't want my parcel data set to have any gaps. Well, that's fine if you're managing a full coverage data set for your parcel layer. But in some cases, we've worked with clients where their parcel data sets have true gaps in the data set. Like, for example, in easement areas or roadways, there's a gap of a certain size. So your validation check may not just be, let's look for gaps. Your validation check might say, let's look for gaps that are larger than a certain tolerance. So searching for those types of gaps. For next example is when you're bringing in multiple different data sources, you're saying that your road geometry must align to your municipality boundaries. So what does that mean, right? Well, your road geometries must not actually cross over a boundary. If it's sharing the edge of a boundary, it must be attributed correctly. And if it's fully contained in a geometry, it must be attributed correctly. And this can be very difficult, especially when your municipalities are being managed by one department and your road center lines are being managed by another. So what you also want to be able to do is not just identify where these issues are occurring, but you also want to be able to, within tolerance, automate the correction of the data. That way, when the data is being rolled up, you're not having to go through and manually correct it every time there's a syncing process. So being able to facilitate these topological rules throughout the workflows. So with that, I'm going to go ahead and just jump into my first demo and see if I can find my mouse. There we go. All right. And what we're going to do is we have two data sets here. We have my street segment data set and my township boundaries. And I'm going to run some validation checks on these two data sets. So I've pre-configured some validations based off of those business rules that I just mentioned before. And I'm going to go ahead and just kick this off. And so within my map extent over here, we have about 20,000 features, and we're going to run these checks across those 20,000 features. So we're going to do somewhere in the order of 400,000 validation checks in about 2 minutes. And basically the reason we can do this is we are taking the data and we're extracting it into our object-oriented disk cache to perform these validation checks. The benefit that this provides us is that we can connect into different sources. So we're not limited to just your GIS data. We can connect to your non-spatial system, your non-spatial database tables, bring those in and bring those into the object-oriented disk cache. Same thing with your CAD drawings, and write those validation checks across the enterprise. But I'm getting ahead of myself. So let me get back to what I'm actually showing here, right? So we're doing those essential geometry checks. So these are typical issues that occur when you have GIS editors entering data. They accidentally create kickbacks and spikes all the time. I don't think there's been a data set that I've looked at where I haven't seen these in a data set. Doing some road centerline validation checks. So these are types of checks that you want to perform if you want to have a routable network, making sure my road names are populated. We don't want to have overlapping roads. We don't want to have roads contained in other roads, looking for overshoots, undershoots, making sure the roads are actually connected at the start or the end. And we can also do these integration checks where we're making sure that my street is actually contained within a township boundary. And if it's contained within a township boundary, it is attributed correctly with the right township name. And then lastly, if it shares the edge of the boundary, so it's sharing that the boundary edge, the right and the left township is attributed correctly. Once we perform these validation checks, we can get a report identifying where all these issues are occurring. So this can drive the end user to these particular issues. So as this is rendering, let's give this a second. On the left over here, we are giving it a conformance dashboard showing us what the quality of the data is. Green is good. It means there's 0 nonconformances. Orange is where we have some nonconformances. And then if we had some major issues, it would be red. All right, come on, let's render.
And Kevin, while it's rendering, one of the things we forgot to mention in the beginning, if anybody has any questions, feel free to put them into the chat, and we'll try to see if we have time at the end to answer.
Yes, thanks, Sheila.
Mm-hmm.
All right, so now that this finished rendering, we can see where all my issues are occurring. And I'm just going to zoom bookmark to a couple of bookmarks real quick, right? So here we're identifying the exact location of where the issue is occurring, right? So if you are if you have a data set that is extremely large, it can be difficult to identify where these issues are occurring. So by pinpointing exactly where it's located can really speed up this process. And same thing here, we have a kickback also. This is where we have an overshoot, right? And notice how I'm pinning the overshoot, but let me just turn these off so I can see it, right? So we can see hopefully this is coming through in the Zoom meeting, but you can see there's a little bit of an overshoot. We're also flagging here is that it's not intersecting at the start of the end, right? So if you're trying to do some sort of routing and it's not connected, it's not going to be able to do that, right? So we're flagging those particular features. If we look at here, here's one feature, here's another, and here's another, but they're not quite aligned. Here's another example where we have an overshoot. And here's an example where the road center line is crossing over my township boundary. So we're going to flag that. And then lastly, where we're validating the attribution. So if I select this particular feature here, we're going to see that this feature is fully contained inside the township of Rochester, but it's attributed with your right township name as Brighton and Rochester. Now you may be saying, well, Kevin, the boundary below here is Brighton, and there's cases where my geometry, my road center line may be offset slightly. So what do you do there? Well, that's these rules can be edited. They're not hard-coded in. They're configurable. So if you have a business need or your data governance policy is saying that even if the road doesn't share the edge, if it's within a certain tolerance of the edge, then it could have the left-right township could be offset based off of that particular configuration. That can be written in the rules engine. So you're not stuck to this core set of validation rules. All this is configurable. All right, so let's go ahead and just while we're here, I mentioned before that when you're dealing with these large data sets and you have data coming and going, you want to automate as much as this is possible. You don't want to have to go in and manually correct every one of these issues. So that's where we can also automate the process of doing the fix-ups. So if it identifies a kickback or a spike, it can remove those kickbacks and spikes. If you have your data governance policy set up where my municipality boundaries are the most authoritative data source, and I want all my road center lines to align to that, I could set up a tolerance. Maybe in this case, I'm setting up a tolerance of 1 foot, and I can auto-align all of my road center lines to that boundary every time that I'm trying to do this roll-up process. Also, I can say, well, if the road center line is completely contained within the township boundary, and I'm okay with it being offset a little bit, being still in that township boundary, I can update that town name. So now if we come back here and take a look, we could see how we've fixed these issues that I showed you before. So automating the process of fixing those, aligning the data set, so now they're all aligned. You know, same thing here, got rid of those overshoots, undershoots. Where the street was crossing over, notice how it's now aligned actually to the township boundary. And then also where the street is contained within, I've updated the attribution here to say that my left city and my right city town name are now Rochester. So real quick, while I'm here, let me just show you what a rule looks like, just so you can see that this. I'm not going to go through in detail all the different types of rules we can write, but just to give you an idea that this is really a configurable interface. Like we could choose which layer or which data set we want to validate against. It pulls in the schema. In this case, we could say the street name must not be equal to null, and this can be extended, right? So we can say instead of null, maybe we want to make this an empty string. And then maybe we want to build on this, so it's not equal to null and not equal to an empty string, right? And you can make this as specific as possible to meet your actual data governance needs. So for example, you know, if I want to say my streets must be contained within a township, I can do that. I could say for all my streets, there's 0 townships where they cross over. Or I could say if the street is contained within a township, the left city town name is equal to the township and the right city township name is equal to the township. And then we have even the ability to do on-the-fly processing of attributes in order to do validation checks. So for example, making sure that roads are actually intersecting the start or the end of a segment. So we can get the ends of a segment and making sure they're actually intersecting. And we do this with what we call built-in functions. All right, so back to the demo, right? So I also mentioned parcel validations. So let me go over to my parcel data set. And what we want to be able to do is we want to be able to find where we have gaps in my parcels that are of a specific tolerance, because we are okay with the gaps where the road center lines are cut through, and also if there's any sort of easement. So here I have a set of rules. Let me select that. And basically, we're going to identify where we have gaps in those particular geometries. But as I said before, we're going to ignore anything that is what we call a true gap based off of the data governance policies that are set by this organization. In this case, they're saying anything that is smaller than 1 meter is a gap. Anything larger than that is a true gap that is okay to have in the data set. So if I come and take a look at some of these results, right? So here we're identifying, yep, we do have a sliver here. If I come over to this example here, notice how we have a gap that's between these 2 data sets. But notice how this one didn't get flagged. That's because this is 1 meter, right? So it's within that tolerance, or it's outside that tolerance. So it's not going to flag that. And then another example over here, I think we have Here's another example, right? It's slight, but it definitely is a sliver in this data set. So we can identify these. And we also have the ability, if we want to auto snap these together, we can auto snap them together. I know people, when you start talking about parcels, a lot of people don't want to edit those parcels. So you can also flag these edits as proposals and then let somebody go through and decide whether they want to accept or reject those particular proposals. All right. So now that we're getting the baseline down, right? So enforcing data governance through validations, let's start talking about some other use cases. Take, for example, if your data governance policy is you want to let the locals be responsible for doing the editing, right? They may be managing all of their local roads, and the state is they're just going to be there to maintain the full state data set. But they also want to still be able to use this data set for doing some analytics, right? So maybe they still want it to be routable. Well, when you're trying to do roll up from the locals to the state, if you have to have it routable, it needs to have proper connectivity between counties. So how do you facilitate that two counties are actually aligned? Well, one, you can write validation checks to make sure they're aligned. You can provide some sort of data governance structure to have the counties work together to align those data sets. Or you can align your data set, and then when you perform your change detection, you just take that into account, right? If you're just bringing up data and not changing anything, you are like literally not editing the data at the state level, you can just do a simple, well, what's different between these two data sets, and leave it at that. But when you start editing the data to provide proper connectivity, you start having to take those into account and making the change detection a little more complex. And that's where 1Spatial can help, because not only can we do the change detection, but we can do the change detection within tolerances. And this is what we're doing at the US Census and a variety of other state agencies. But it can get even more complicated than just dealing with edge matching. What happens when the locals are managing the data for E911 purposes, and their computer-aided dispatch system requires the data to be in some different format than the way the state's maintaining it? And we see this a lot. So if you're looking at these two pictures here, right, the picture on the right, the data has these pinch points, right? The computer-aided dispatch system requires these pinch points, but the state network, they may be maintaining the data with a crisscross. And then sometimes you have some locals maintaining the data like this and others maintaining it like this, right? So how do you take that into account when you're trying to do the data roll? Well, what we can do is we can on the fly update the local network to make it appear to be what the state data set looks like, and then perform the change detection at that point. That way we're only updating these things that have actually truly changed, and not just in a different representation of those data sets. So let's go ahead and just show you this example now. So in this case, I'm going to show you the data first, and then we'll run the analysis. So here I have two different data sets. I have my state network, and I have my county data set. If we zoom into some of these example areas, you'll notice that the data is not necessarily completely lined up, right? It's slightly offset. So this occurs when you have two different entities editing the data, maybe in two different projections. When you're trying to reproject everything, things get slightly shifted, right? So when we're doing the change detection, we want to make sure that we're taking that into account. So this may not be a true change, right? So what we're going to do is, let me go back out here. All right. So what we're going to do is we're going to run some change detection on this data set. So I'm going to flip over. In this case, before we were using OneIntegrate for ArcGIS, I'm going to flip into our OneIntegrate Enterprise product. And this is outside the discussion of which ones you should use, but maybe I'll get into that later when I have more time. But anyway, so we're going to pull in the data from the Maryland, from this particular state data set. So we have some routes and we have some county data sets, and we are going to perform my change detection. Now, these data sets could be coming from the same database, or we can be coming from two separate databases. My next example will show bringing in data from multiple different sources, but just for simplicity's sake, in this case, they were both in the same database. And so what we're going to do is we're going to do a matching algorithm in our OneIntegrate product, where we're going to look at within a tolerance, does the state match the county, and does the county match the state? we're going to use a bearing check. And we're also, no, in this case, we're not going to do an attribution check because there's no attribution in one of the data sets. But if there was attribution, we can also take attribution into account. Once we determine those interactions, we then can build out our match. What's a match? What's a reshape, meaning the geometry has changed? What's a delete? And what's an add? So if I go back, I've pre-run this. So if I go back and take a look at those results, we can identify where all the changes are. So for example, if I go over to where I was before, right? We can see that even though this is offset, it's still being flagged as a match because it's close enough, right? It's within that tolerance that we set, which is configurable. If we come over here and look at where we have an add, right? So if I turn off my proposal layer, here was the state data set, there's the county data set. Notice how we now have a new feature, so that is an add. And then here's an example where we have a delete, right? So it was in the Maryland data set, but notice how it's not in the county data set anymore, right? So that's why it's being flagged as a delete. And then we also have examples of where we have it reshaped, right? So if I come over here, here was my original state data set. There was a new route that came in here. And because of that, this road extended out to that intersection. So not only do we get an add over here, but we're gonna get a reshape here. So that's why we're flagging that as a reshape. Now this all looks like it's working pretty well, but what happens when we start to get to some more complex situations, like where we have like a pinch point, right? So notice here, we have a pinch point, and when I'm trying to do the comparison, I'm getting different results than what I would expect. There's some adds in here. So why is this happening? Well, we're getting outside that tolerance. We're also, our bearings are changing because of these pinch points. So it's causing some issues with the change detection. So what we want to be able to do is be able to take this into account when doing the change detection. Same thing over here where we have a three-way intersection, or maybe here's another example of a three-way intersection, and then here's a four-way intersection, right? Same thing, we're getting all these adds when they're really not adds. So what we want to be able to do, let's go back to my first pinch point, right? Is we want to, on the fly, identify where these are occurring and update the data set so that it is actually represented the same way that the actual state represents it, right? So now I've updated that data set, and we're not doing this, we're not pushing anything into an additional database. We're just gonna do this on the fly in the engine itself. We're just, at this point, we're just visualizing these results just to show you what I'm doing under the hood of the application. So then basically, once we identify what the network should be represented as, we can then do our change detection. Now notice when we do the change detection, we're getting our matches over here. And if I come back over to some other examples, there's other examples. Let's see here. Here was where we had that three-way intersection, right? I updated the data set. And once I updated the data set, now in this case, this is offset outside that tolerance. So that's why it's being flagged as a reshape. And then here's another example, right? So here was the original representation. Here's when we updated it. And then when we perform the change detection, notice how we're getting matches now. So it's telling us nothing's changed enough outside that tolerance. And then this last example here, same idea, right? Original representation, how we are representing it before doing the change detection. All right, so by doing this, we can not only do the change detection, but we can determine how different something is, and is it different enough to warrant a change upstream into the state network, because we don't want to have to do all that additional cleanup every time we're trying to do a data roll-up process, especially when you're dealing with a state that may have 50 or 60 counties, right? That can be not an easy task. All right, so switching gears a little bit, what happens when we're starting to deal with non-spatial systems like CAD-based systems, and we want to take that CAD and bring it into our GIS, right? So anybody that's worked with CAD drawings and try to bring in the GIS, they realize that it's not a simple process, right? A lot of times your CAD drawings are in paper space and not geo-referenced. So how do you get that CAD drawing into your GIS? And if you're lucky, you may get a WLD or a world file, and that will have 1 or 2 reference points. But even if you have those 2 reference points, the data is still going to be shifted throughout the drawing. So it's still not going to align correctly. So you still need to do some sort of data alignment process at that point. And then lastly is a lot of times your CAD drawings are actually schematic representations and not real world representations or not GIS representations. So there needs to be some sort of conversion to go from your schematic representation into your real world so you can do analytics against that data set, right? The reason why you're trying to take your CAD drawing and bring it into GIS in the first place is so you can do GIS analysis against it. So it needs to actually be aligned to your GIS data. Now, we can handle this in a variety of different ways. If the data has some sort of geospatial referencing information in it, we can use things like positional accuracy improvement to identify shift vectors to shift the data to get it into place. Or in cases where it may just be all in paper space, we can use information from the objects in the CAD drawing to identify where it needs to go into the GIS and then perform the shifting based off of a rules-based approach. So basically identifying how your governance should work and facilitating that into a rules-based approach. So let's go ahead and just take let's take a look at this example here, right? This is some work we did at NASA, and in this case here, we have a CAD drawing. This is what we call a butterfly drawing of a manhole. So imagine this being a box and you just step on the box and open it up, right? And this is the wires that are running around that particular box. So what we want to be able to do is we wanted to be able to take this drawing, migrate it into the GIS, align the wires with the electrical line so we can start running actual analytics against the electrical feeds in the drawing. And obviously, we're not just going to move one manhole. You don't have one manhole in a facility. You may have hundreds of manholes. So you need to be able to do this in an automated process to make sure that you can facilitate this in a quick manner, right? And not only that, is that the data is not stagnant. You're not going to just bring this in once and this drawing is never going to update again. These drawings are going to be updated as things change in the field. So you still need to be able to facilitate bringing the data in, doing a change detection once you get it into the system. So the more you can automate, the less of a headache this is going to be in the future, especially when you're trying to keep all your systems in sync. So with that, let's go to the next demo. All right. So basically what I'm going to do is I'm going to connect to a DWG drawing, right? So within OneIntegrate, we can connect to more. Oh, of course. This, let's see here. Let's try this one more time. Okay, all right. Oh, live demos, you never know what's gonna happen. All right, so what we're gonna do here is we're gonna connect to a DWG drawing, right? In this case here, this is the drawing file. We can connect to that DWG drawing. We have the ability to not just connect to DWG, we can connect to Bentley file, CSV, enterprise geodatabases, file geodatabases, shape files, map info, non-spatial systems like SQL Server, Oracle, Postgres, or their native spatial types. And this is just a subset. You can extend this out if you so desire to connect to other different data sources. And when you connect to that, it brings in the schema of the data set. So if I flip back to my session, this is where we're running the analysis. I can take a look at what I have in my drawing. So I'm going to flip over here to my map. And notice when it brings this drawing in, this is what you typically get with CAD, right? You get a bunch of line work, and this is spread out between just 3 different layers. We have a layer for the manhole data. We have a layer for the wiring, and we have a layer with the labels. So these labels identify which feeder this particular feeder line is reading to. So before we can even worry about migrating this into GIS, we have to extract out the features, and we can do this using a rules-based approach. So basically, we're going to identify where my floors are. We're going to identify where the walls in the drawing are, the ducts, and so forth. And then we're going to pull and get my feeder information. So identifying which feeder is along the line, right? So now we at least know what we're dealing with in the drawing itself. But notice here, if you look in this lower right-hand corner over here, you're going to notice that this is in paper space, right? This is not in GIS space. This is not on Null Island, right? It's in GIS space. So we got to take this and move this to get it into my GIS. So if I come back over here, the next thing we're going to do is we're going to connect into my GIS data set, right? So in this case here, I have all of my electrical work in a file geodatabase. We're going to connect to that. And then what we're going to do is we're going to align my CAD drawing to that GIS using attribution that's in the CAD drawing to try to get the best fit to the GIS. So let's see here. Now let's take a look at this. All right, so now we can see that we are now aligning the CAD drawing into the GIS. Now, what went into this, right? Well, one thing we had to do is we had to look at the manhole information in the drawing. So my manhole number is 1564. So we pulled that information from the drawing and brought the drawing over here. And then what we did is we shifted the drawing around until we got the best fit. And using the rules-based approach, we validated every time we shifted the drawing or rotated the drawing, we validated to make sure it was the best fit. And then once we identified what the best fit was, we could apply it to all the objects and bring them into the actual GIS. But as I said before, right, this is not doing us any good. We're still a schematic representation. We can't do analysis against this. So that's where the next thing we needed to do is we have to actually take the data and make it so that it actually fits into the GIS space. So getting that information, aligning it to the electrical network, identifying how many times the wiring is rotating around the particular manhole to get proper estimates of the actual length of the drawing, which all can be fed into your modeling software that you have. Now, if we come back now to the drawing here, what we're going to notice here is that we actually have, not only do we have I have so many different layers going on now. Let's see here. Let's take a look at the actual GIS, right? So here are the GIS layers, and then let's look at the integrated wiring, right? So if I select one of these wires now, right, we're going to see that we have multiple different feeders, right? Because there's multiple feeder lines, and each of these feeder lines are actually connected now to the electrical network, right? So now we have applied this to one particular data set. What we need to be able to do is now apply this to all of the drawings. Now, I'm not going to run it for you guys for every single drawing, but I'll just show you those results right now in a GIS. So we brought in this example. You already saw that example. But what about another example, right? So here's just another example. Applying those same rules on all of the drawings so that we can do this for the entire network, pull in for the entire network, and then connect the feeder lines. So now we have our feeder lines, and we can follow that feeder line from one location all the way around the entire network. And we can apply this for all of our feeders. So we have that information built in. So now we can actually do the geospatial analytics, which is why you have a GIS, right? You're going to apply that geospatial analytics to that CAD drawing. But then if there's some sort of change in the CAD drawing, you can facilitate that roll up since you're doing this in an automated fashion. All right. Almost done. One more demo. All right. Now let's go back full circle, right? Remember the first example I was talking about and the at the VA where we had missing address information between my facility management system, or sorry, my emergency management system and my web map, my GIS system. So how can we stop this from happening? Well, one way we can do it is performing an address matching between those two systems. And we've actually done something similar at the US Census Bureau where we're doing an address matching or matching the partner addresses that are being submitted up against their master address file. So identifying what's different. Now, just like you're dealing with a GIS, right, you need to do an initial validation before you're going to do any sort of change detection. So where are their null records? The partner data set, a lot of time, it's coming in as a CSV file. So there's going to be a lot of leading and trailing spaces. So identifying where those exist, and then even auto-cleaning that information, so providing a cleansing task. There may even be duplicate addresses, so identifying where do we have duplicate addresses. And then once we do that, we can perform the change detection. But when we do a change detection, we're not just going to say, okay, well, these two streets have a different string name, so they are actually different, right? We need to be able to build tolerances in that, so we can apply different algorithms to determine how different two streets names are from themselves. So for example, you may have a main street written out as like main, M-A-I-N, and then you may have a main street written out like the state of Maine. Now, when you perform the change detection, you want to know that these two it may just been a typo. Somebody might have mistyped it. So you can check these and give it a weight, right? So we do, in this case, we're using a soundex function. So does it sound like each other? We also have functions that are determine how different two strings are, like the Jarrah-Winkler similarity model and the Jarrah-Winkler similarity model and the Levenshtein distance model. Right, so you can use these functions, and you can look at we look at each individual attribute that makes up the entire address and gives it a weight on each one of those attributes, and then from that we can calculate our total confidence of whether we have a match or whether this is a new record in the data set. And then with those confidence scores, you can adjust what is an acceptable confidence score to facilitate what is different between these two different data sets. If you so desire, you can also set it up where you could say, well, anything that is 90% and above, we're going to automatically say that's a match. Anything from 90 to 75%, we want to have some sort of manual review process. So just those few records, you can submit that for manual review. And then anything less than that gets automatically rejected or it gets automatically put in as an add. All right. So real quick, I'm not gonna run the I'm not gonna run the results. I'm just gonna show you it just for time's sake, right? So here I have a CSV file, all right? And this CSV file, it has information. It has street name information. We don't just have one street name. We have multiple different street names. Now, if any of you guys are really paying attention right now, you may notice, hey, Kevin, I know there's no such thing as an alpha road. Well, we're actually, in this case, we're using our unit test to perform this analysis because U.S. Census and U.S. Census and Title 13, I can't show you their actual data, right? I don't even have access to their real data. So these are just the use cases that we built internally before we deployed it at the U.S. Census on their actual data set, right? So anyhow, we have our partner information. So this is all the address information. We also have my master address file with the street name information. And then what we're going to do is we're now going to compare these two different data sets to see what is different between these data sets. And as I said before, I already ran this, and so I'm not going to open it up and run it again, but I'm just going to show you what the results would look like, right? So comparing these two different data sets, we give it a total confidence score. So one means it is a near exact match, right? So my partner address in this case was 2 alpha. The Math Tiger was also 2 alpha. So this was an exact match. Where it gets interesting is when we start seeing things that are a little bit less than 1. So take, for example, here we have a 99% conformance, and we have 7 Richmond, and we have 7 Richmond, but it's spelled slightly differently, right? So this is why we're flagging it. But at this point, we can say we can pretty confidently say, well, this is a match. And we're going to ignore this when we're going to do our doing the add or bringing in the new data sets. And then as we get further and further down the conformance levels, we start seeing things aren't quite matching, right? So in this case here, the zip codes are slightly different, which is why it's getting an 80% conformance. So in this case, we would probably just say, well, if it's anything less than 90, we're going to go ahead and reject that. Or I should say, if it's less than 90, these are not an actual match. This is a new address, and it should be added into the Math Tiger data set. All right. So by connecting into these different systems, right, we have a CSV file, and we have our data. In that case, that was in an Oracle database. We have these 2 different files. We can compare them, see what's different between the 2 of them, and facilitate when there's a change, what do we do with that particular change? So if we go back to that first example at the VA, we could have identified, hey, these two addresses are different. I'm sorry, there's a missing address in my GIS. Let's go ahead and geocode just that address that's missing and add it into my GIS so that it's actually showing up in the case of an event. And we've been able to identify that issue well before the actual event occurred.